So let's just go back a little bit and try to remember what we were discussing last time. So if you remember, we started with mechanics of failure, and one of the things that I hope you are convinced now is that if you have a sharp crack, you will have larger stress concentration at the tip. And there is a formula relating the maximum stress at the tip to the average stress, and you see that the relationship has a reciprocal relationship with the radius of curvature, which means that if the crack is sharper, you will have larger stress concentration. And of course, if it is not as sharp, you have less. And I told you at the end that what you want to prevent or avoid is always having sharp corners or very abrupt changes in geometry, because your stress concentration factor may be then very large. So now, today we want to talk about crack propagation, very related topic. So if you have a sharp crack in a brittle material, it's going to propagate very, very fast. If you have a ductile material at the corner, because the stress is maximum, you are going to have yield. And you have a deformed plastically deformed region here, which makes the crack less sharp. And that's one reason in ductile material we have this warning phase where the crack doesn't propagate as fast. What happens is that at the tip of the crack, basically the energy which comes from the stress, it wants to balance itself with the work that it's doing. And the work is creating new surface. So as the crack propagates, new surface is going to be created. If you have taken thermodynamics, maybe this is energy balance is familiar to you. So you have a stress, and at the crack tip, then there will be energy balance, and the more stress you have, the more surfaces will be created. The crack will propagate very fast. So it shouldn't be any surprise to you that the critical stress, which if it is exceeded, you are going to have propagation, has, for example, a term, it is proportional to a specific surface energy. Does anyone remember the definition from thermodynamics? Specific surface energy? That's the energy which is necessary to create a unit surface area. Elastic modulus, and of course, it is also related to the size of the crack. So the smaller the crack is, it becomes less critical. The larger it is, more critical. Now, the size of the crack, the way we define it, it depends if the crack is internal crack or a surface crack. Remember that when it is internal, basically it is 2A, and here is A for the crack size. Now, what is important for us is we want to prevent this brittle fracture. We want to design such that we don't have this kind of crack propagation. There is a very important parameter related to this phenomenon, which is called fracture toughness. This is a measure of resistance to fracture propagation, resistance to brittle fracture propagation. Let's see what are the components. There is Y, which is a factor. It depends on the geometry of the specimen, geometry of the crack, etc. there is a stress, and then there is the size of the crack, which depends if it is internal crack, it's 2A. If it is surface crack, it's just A. Now, before doing some examples and getting to know this equation better, because that's something you can use for design, let's first think about the unit of fracture toughness. What do you think the unit is? What's the unit of fracture toughness? It's a strange unit, but that's the unit. What's the unit? I'm telling you that y is dimensionless, doesn't have a unit, like a string. It's just a scaling factor. It depends on the geometry. Stress, what is the unit of the stress?
Force per area.
Force per area. So it's like megapascal, psi, something like that. Pi is a number. How about crack length? Meter, something like that. So the unit turns out to be something in the form of, for example, megapascal meter to the power of 1/2. It is true. That's why I said it's kind of unusual. Sometimes you see it written like this. You may see it written like this. Of course, this can be they have to match. So if you are using inch here, it is inch there, but this can be psi, this can be some other, like kilopascal or something like that. The second question is, do you think fracture toughness is a material property? Someone is shaking his head saying no. Is it a material property? Everyone is shaking their head saying no. Why not? Why are you shaking your head saying no? Which is true. Why not? Why not?
It's dependent on crack length.
Yes. It depends on the crack length. And it also, so it depends on size. It depends on geometry. Also why? This has geometry of the specimen and the crack. So the answer is correct. It's correct to shake your head. It's not a material property. However, it turns out that if the crack is much smaller than the size of the sample, if you have a situation like what I was showing you just a bit earlier, like compared to the size of the sample, your crack is very tiny. And this is typically the case in engineering. You have millimeter-sized crack, micrometer-sized crack in a big piece of machinery or a big girder. So it turns out that if you have plane strain conditions, which is like one dimension much larger than the other, and if you consider just this mode of fracture, which is opening the crack face perpendicular to its axis, just opening it up, the fracture toughness for this particular situation becomes independent of the geometry. And then we call it plane strain fracture toughness. And we put this I here. This is like the Roman number, like for the first mode of fracture. And this is actually a material property. A material property, you need to have a way to measure it. And this is how people measure plane strain fracture roughness. look at first the little sample here with the notch. So it has a standard size, etc. It has a little notch. And then you put it here and you send a hammer from an initial height to crush it basically, and you measure where it stops. From the initial height and the final height, you can calculate how much energy actually was needed to fracture this specimen. It's called Sharpie. It's after someone. And then this gives you the fracture toughness, the plane strain one. So there is a way to measure it. And we can also look at the values for different classes of materials. These are our favorite classes: metals, ceramics, polymers, and composites. And just looking at the graph, you can see that metals have a large fracture toughness compared to ceramics, for example. Look, concrete is here. Steel is up there. And then composites have a wide range depending on the structure. But this is no surprise. You know that concrete cannot take so much fracture energy. So we are not surprised about that. Anyway, I told you that this equation is useful to design for fracture, or to design such that we don't have fracture. How? Well, you either want to make sure that the stress here is small enough not to reach the critical stress and not to cause fracture. So you don't want to be here, you want to be here. Or you want to make sure that the size of your crack is small enough that in the combination with the stress, that it falls somewhere here and not here. And this equation is basically nothing else but the equation that you see here, relating the fracture toughness to a stress and to crack size. So now putting this together, basically you either design for a stress, if you know you have a certain size cracks inside your material, you have some tolerance for certain size defects, or you know what is the stress that you want to design for, and you say, okay, we want to make sure that this piece of equipment or this girder is not going to have any flaws which are going to be larger than this value. Is this clear? Now let's do a few examples to make sure that this is all clear. The first one is more conceptual. So we have a large plate which satisfies this plane strain condition, and we have a flaw inside. The question is, which one of these factors do you think has the least influence on the fracture load? I pass around an attendance sheet. Just decided one, two. So please make sure you write your name and initials. So you can talk to each other and decide which one of these have the least influence on fracture load. It has a big influence. Fracture toughness. So I guess we are somewhat between elastic modulus and yield strength. Elastic modulus is a part of when you calculate the critical stress for crack propagation. So it has some influence, but I would say both of them have a lot less influence than A and C. Now, the next question is the same cartoon, the same schematic, but the question is different. The question is, let's imagine that you have this and you see that it fails at the failure load of P. Now, what happens if the flaw size is double? First of all, intuition. Will the force be larger or smaller? If the flaw size is larger, the failure will be lower, right? So now let's try to see if you can calculate it. The hint here, or something that you have to pay attention to, is that K sub IC is a material property. So it doesn't change when you compare 10 millimeter to 20 millimeter. And Y also, because it's, you can assume that it is the same for both cases. Now try to spend a little bit of time, talk to your neighbors, however, and see if you can get to the right solution. Right now the equation for 10 millimeter and 20 Well, of course, I have to see three correct answers. I see one correct answer. second correct answer. Yeah. Okay, I've seen three. Okay, so I write this quietly, and if you are working on it, continue working. If you want to check, you can look. So this is what we know. And it's good to write down the equations. It makes us remember them better. So this is what I believe. In this particular case, if you didn't divide this by 2, you wouldn't get a wrong answer. But if you were looking for an absolute value of something, you would get a wrong answer. And I'm using the same unit on both sides, so it doesn't matter. But you have to be careful about units otherwise. So here it would be so this is normal stress, so I can very easily, and this F is for failure, so it's normal stress at failure, so I can write it as force at failure, which is given as P over A. This was a FE question. You could have just done a simple calculation and chosen the answer. If it is the 56 question, you need to write something down. So just saying this is not probably work very well. If you are done with this, while some of your friends are maybe writing, please look at the next problem. Very straightforward. Divide by 2 because these are both internal cracks. You see it in the shape, this is a schematic. Maybe I write down here. In your homework, I think you have surface crack. copying from the so straightforward. So basically, if you look back a few slides, I come back here, don't worry if you didn't. I kind of showed you that, you can have, with this equation, you can have either case for design. So for every level of stress, you kind of can calculate what will be the minimum length of fracture. If it is larger than that, then it will go in the fracture. So if I look at every stress level, there is a minimum length before fracture, and then if the flaw becomes a little bit larger, then you are going to have fracture. So that's kind of an example like that. So I made this schematic here, and the way we find out basically the equation of this line is this equation. So we know the plane strain fracture toughness. It's important to know what parameter is what in English. The plane strain fracture toughness is here. And then we want to see at this stress level what would be the critical length of the crack to have fracture. It's easy to find. So you can see that. Yes, please. Good question. This is a surface crack. So it's a good question. I forgot to emphasize that. Thank you. So if the crack is surface breaking, A is just this. If it is inside, like it was in the other cartoon, in this equation, half of it is the crack. And you can kind of see why, right? This one looks like 12 back together. Something to remember. But thank you for bringing this up. I totally forgot. Any other questions about this? Now I hope that you see the size of the crack matters a lot. So if you have, let's say, I showed you the Minnesota bridge failure. So if you have a girder or a bridge, you should be worried about developing cracks on your bridge. It turns out that there are ways to measure the size of the cracks. Unfortunately, in civil engineering, the state of practice is the field visual inspection. I don't know if any of you has worked for 10 years as an inspector. Yes, just visual. So basically, people go and look at this. But fatigue cracks, maybe I bring you a sample. Fatigue cracks you won't see. They're extremely small. So this is not the best way. In other industries, like in aerospace or planes or in nuclear industry, they have higher standards. Of course, there is much more at stake. You don't want a plane you are riding that all of a sudden there is a crack propagation and so on. So I think I told you that actually this is very much related to the research I'm doing. So there are ways that you can have sensors which can very easily size and detect cracks. So for example, last year we had a project, a nuclear-based container. I don't tell you exactly where it is, but there were some concerns that maybe there are some cracks in this container developing, and there is concern that they propagate under stress, and then you have leakage of nuclear waste. A big problem. So you can have instruments to go there and check and size and make sure that everything is okay. So that you get some ideas what you are learning, how it is actually related to practice. So a very basic method is just like when you go to a doctor, and hopefully you haven't had it, but you have heard probably ultrasonic imaging. So you can go also on a bridge, or you can go on a piece of material, and you can send in ultrasonic energy. If there is no defect, then all the energy is going to come back from the other side of the structural membrane you are testing. If there is defect, then you are going to see some signatures. And that's something that we are doing. And there are now ways that you can be very far from an object, and you can send the wave, and you can actually measure and map the cracks and monitor their growth. So, giving you some ideas how this works. Okay, now with that, we switch gears and we start talking about packaging. So, we are talking about mechanics of failure. Started with brittle versus ductile failure, and then I hoped I brought some ideas from fracture mechanics to your knowledge, and now fatigue. Fatigue is a failure which happens when you have cyclic loading. So cyclic loading is when loading is actually repeating itself. Now between maximum and minimum stress, you may have an average which is not equal to 0, and this is called the amplitude of a stress. How do we test for that? You typically have a coupon, and you apply many cycles of loading, and you go from positive to negative tension to compression, and you see when the material fails. There are a few definitions that we need to learn in relation to the fatigue loading. One is the range of a stress. So when the stress is changing from some maximum to some minimum, the range is of course maximum minus minimum. The average stress or mean stress is half the summation of maximum. And that is the green line you see here. So here, for example, if I would draw the range, and amplitude is half of the range you see here. This is very important in some of the graphs that you see later. Everything is based on the amplitude. And then we have a stress ratio, which is, this is minimum. The ratio of the minimum to maximum stress. So maybe in the next one. So this is random loading, and these are periodic loading. You have seen this before. So we call this periodic. And let's say if this maximum was at 40 and the minimum is at negative 60, and for us positive is tension and negative is compression. If the stress was oscillating between 40 and negative 60, let's calculate these parameters that we just defined. I give you a few moments, just a stress range, for example, just the parameters from the previous slide. Try to just calculate them, see if it makes sense. Let's use megapascal here, for example. Is there anyone who didn't sign his name? So a stress range would be sigma max minus sigma mean. How much is it? 100, right? 40, don't forget the signs. And you see visually that it makes sense. You need to take into account the signs. The range is actually 100 megapascal. It's not really. So mean or average stress is 1/2 so it is 1/2 it doesn't match the figure, but negative. It's compression. Negative or compressive mean stress is good for fatigue. Remember, what we don't like is tension. In fatigue or generally in brittle fracture, what makes crack propagation is when you have tensile force which wants to tear apart a crack. So if you have a crack here, what you don't like is to have the force which pulls it apart. If it is compressed, it is actually good because it's closing the crack, so you don't have issues. You'll see later that we try to use methods to have more negative stresses in material. We get that there. How about a stress amplitude? This is half of the range, and this is 50. And then the ratio, depending on how you define it, if you take minimum as the negative and maximum as positive, this is a negative number. If you have a fully reversed situation like that, you have negative 1. That means it goes to positive, negative, and that's kind of a really bad kind of loading, because it puts the structure into these cycles of positive and negative, and it facilitates failure. These are the definitions. Does everyone have this written? Now, you've seen this before. So here, I hope that when we say a stress amplitude, it is more clear to you what that is. The top of the range, depending on how the stress is fluctuating. And then we are looking at number of cycles to failure. We talked about this before. So at a particular stress amplitude, if you count the number of cycles that cause failure at that stress amplitude, this number of cycles is called fatigue life. What is important to understand about fatigue is that the material may be much stronger if this load was not so repetitive. But as you repeat the cycles, the material becomes less and less strong. It loses this maximum stress that it fails. It becomes smaller, as you can see. Depending on the material, we are comparing here steel and aluminum. If you have a steel, after a certain number of cycles, the stress at failure doesn't change anymore. Does anyone remember what we called this before? Fatigue limit or endurance limit. So if you want to see if a point is, if a stress condition is safe or unsafe, you kind of have to see where it falls. If you know how many cycles that material or a structure is going to tolerate and at what stress level, then you kind of have to look at this point and see whether it is safe or unsafe for that particular material. One of your homework problems is asking something like that. And here are some other, you see, depending on the material. Now, we are looking at other alloys and other material, and you see that they can be different. Depending on the material, you have different kinds of curves. Maybe we'll still have time to do this example, it looks like. Okay, we could after also stop here and start. If you have any questions, we have 2 minutes. Okay, it's fine.